Uh, Welcome to everyone for this Ramanujan Yatra lecture series. As we have been conducting from Vigyan Prasar from past few months, we have been organizing lectures about Ramanujan in various Indian languages and also in English, inviting international experts. Uh, in the year 1920, April 26th, young Ramanujan passed away. This is the 100th anniversary of his death. To pay homage and also to remember Ramanujan's memory and also address the issue of maths phobia and also popularize mathematics. Vigyan Prasar has been organizing a major program called Ramanujan Yatra. We wanted to organize a nationwide program reaching a lot of people, but unfortunately, due to the pandemic situation, we were not able to execute many of these activities. However, we decided to conduct webinars in Indian languages, popular lectures, so that large people can be given access to Ramanujan's thoughts, ideas, and relevance. And also, we are inviting international experts, people who have worked on Ramanujan's mathematics, his life history, uh, to give lectures about Ramanujan and his legacy. Today, we have with us Professor Andrews. Before I proceed, I would like to invite our director, Dr. Nakul Parasar, director of Vigyan Prasar, to explain about Ramanujan Yatra. And then Dr. Ramanujan of Institute of Mathematical Sciences will introduce today's speaker, and then we will have the lecture. So I would request our director, Dr. Nakul Parasar, to introduce Ramanujan Yatra. Sir.
Namaste, namaskar. Very warm good evening to everybody here in India, and a very warm good morning to everybody in the US and in the other parts of the world. It gives me an immense pleasure to welcome all of you to today's edition of Ramanujan Yatra, where we have every month we have an expert who agrees to join us, deliver his talk on Ramanujan. Ramanujan Yatra is basically a series of programs that were conceived under the leadership of my able colleague and most dearest friend, Dr. T.V. Venkateshwaran, in collaboration and in close support from Dr. Ramanujan of the Indian Institute of Mathematical Sciences. We decided that it's the 100th year, as Dr. Venkateshwaran just said. On 26th of April 1920, uh, young Ramanujan passed away, the young legendary mathematician passed away, and as a result, we all decided that this year, being the centenary year of his passing away, we'll organize events from April 26th to December 22nd. December 22nd happens to be his birthday and is celebrated in India as a National Mathematics Day. So this entire period was divided into different. We had all these months: May, June, July, August, September, October, November, and December. And we decided that we will have programs all over the country. But it was we had first meeting. We had meetings in the place in Delhi, where we decided that we will have a lot of these programs all over the country. But ever since lockdown came, we were forced to follow the new normal. We were forced to go the online and the virtual way. I wonder if the idea was to reach out to a number of people, but I wonder, with this new online uh, platform, I'm sure we have reached out to much more people, and for every program that we have organized, I think we had people who could join from anywhere and any part of the world. In today's, so we had lectures, we have compiled books, we had written articles in our regular newsletters every month. We come up with an article in different forms, whether it is in one language or another. But we have been covering Ramanujan Yatra extensively in our different platforms, whether it's print, electronic, social, or digital. So, without taking much of your time and without coming in between Professor George Andrews' lecture that we are all anxiously waiting to hear, I would now pause and would now leave the floor open to Dr. Ramanujan to please welcome our distinguished speaker today. And we are all very anxious to hear you, George. And we really, on behalf of the Gyan Prasad Department of Science and Technology, Government of India, we heartily welcome you and we feel very proud and thank you for accepting our invitation to deliver this keynote lecture today. So thank you once again, George, from the entire team of Vigyan Prasad. And also thanks to Dr. Ramanujan particularly, for he has been the man behind all our lectures that we've organized so far. We remain indebted to you, Dr. Ramanujan, for your support, love, support, affection, and your passion for this Ramanujan Yatra. Last but not the least, I would credit all of this to my most dearest and most respected friend, Dr. T.V. Venkateswaran, for having initiated this idea, and the entire group under him of Sri Kumar and Bhaskar to ensure that we do it regularly. So once again, thank you so much, and I'm sorry for having extended it. After saying pause, I've still gone on and on. Unfortunately, have been a teacher, so I don't stop unless my 40 minutes get over. That's my pet sentence. So forgive me for that. So over to you, Dr. Ramanujan. Thank you.
Thank
Namaste.
you. Thank you. It's my pleasure to introduce the speaker of the day, Professor George Andrews, an eminent American mathematician who's Ivan Pug, Professor of Mathematics at Pennsylvania State University. And he's known all over the world, in fact, perhaps considered the world's leading expert on integer partitions. And he works on number theory, combinatorics, analysis, special functions, and very important for this particular lecture series is that he was the person who discovered Ramanujan's lost notebook, and he's going to tell us about it. I must also mention that Professor Andrews is highly interested in mathematical pedagogy, and I've particularly enjoyed reading some of his writings on that. Um, uh, he's a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, and a fellow of the American Mathematical Society. He has been invited speaker at the International Congress of Mathematicians. He has been honored with honorary doctorates by many universities: University of Parma, University of Florida, University of Waterloo, University of Illinois at Urbana-Champaign, and our own Shastra University in Kumbhakonam. It's great to have a distinguished mathematician and a Ramanujan scholar here telling us about Ramanujan. And thank you very much for accepting our invitation, Professor Andrews. Over to you. We look forward to hearing you.
Thank you. Now, can we have the slides on the screen, please?
Yeah, I'll share the screen. Just one second. Yeah. Srikumar, screen share, Amma.
Okay, so thank you, Dr. Ramanujan. Thank you, everyone involved in setting up what is obviously a difficult procedure to make this work internationally. I'm grateful to all of you and to those of you especially who have figured out how to make this this project work with the difficulties in getting the slides up. So I'm very glad to be here. The talk is titled Ramanujan's Lost Notebook in 5 volumes, Some Reflections. So that's dedicated to the memory of Ramanujan, who died 100 years ago. Next slide, please. So first I want to give a little background. Next slide. So this is this stamp that was put out in honor of Ramanujan on basically when would have been the 75th anniversary of his birth. A number of stamps have been put out subsequently, so I hardly need to tell an Indian audience that Ramanujan is a national hero in India, and he is certainly a great hero of mine. Next slide, please. So there it is. There was almost. Okay, so this is the cover of the book that is a decades-long project that Bruce Barrett from the University of Illinois and I have undertaken. I will only tell you that the Ramanujan's Lost Notebook, which I'll describe a little bit of the background on subsequently, has formed a significant component of my career. And about a year ago, the part 5 of this 5-volume work came out to explain the 120 or so pages that constitute Ramanujan's Lost Notebook. And next slide, please. So what I want to tell you about is a little bit about how I got involved with the Lost Notebook before I tell you some of the treasures that are within it. Next slide, please. So this is an interview of Ramanujan's widow, who lived into the 1990s, lived to a very ripe old age. And she speaks of his last year of life as follows. He returned from England only to die, as the saying goes. He lived for less than a year. Throughout this period, I lived with him without break. He was only skin and bones. He often complained of severe pain. In spite of it, he was always busy doing his mathematics. That evidently helped him to forget the pain. I used to gather the sheets of paper which he filled up. I'd also give him the slate whenever he asked for it. He was uniformly kind to me in his conversation. He was full of wit and humor. Even while mortally ill, he used to crack jokes. One day he confided in me that he might not live beyond 35, and he asked me to meet the event with courage and fortitude. He was well looked after by his friends. He often used to repeat his gratitude to all those who had helped him in his life. So this is a description of really what the last year of his life was like. Next slide, please. And in the one letter he wrote to G.H. Hardy during that year, he did not discuss his health at all. He had returned to India in the hopes that being back in his home country, his health would improve. Unfortunately, that did not turn out to be the case. But all he really talked about in his letter to Hardy was the following. In this letter, January 12th of 1920, I'm extremely sorry for not writing you a single letter up to now. I discovered very interesting functions recently, which I call Mach theta functions. Unlike the false theta functions studied partially by Professor Rogers in his interesting paper, they enter into mathematics as beautifully as the ordinary theta functions. I am sending you with this letter some examples, and he lists a number of them and gives a number of relationships in the remainder of the letter. Next slide, please. So this is part of the manuscript that he was writing and that his widow describes in that interview that I just read to you. This actually is from the last letter that he sent to Hardy. This is his own handwriting, and it shows that he lists these Mach theta functions, talks about some of their properties, and talks about relationships among them. Next slide, please. So this is the final page of this letter. in which he actually relates. He has three classes of functions that he calls third order, fifth order, and seventh order. The most mysterious of all are right down at the bottom of this page. I will describe them more in detail later. These are the seventh order functions, and his last line is, these functions are not related to one another. Sincerely yours, S. Ramanujan. Next slide, please. So, in 1976, I was visiting Europe and England, and on the advice of Dr. Lucy Slater, visited the Trinity College Library, where in boxes that were contributed by G.N. Watson, this lost notebook I was able to find this and realize that this was the background for the letter on Mach theta functions, which he'd written to Hardy. I inquired with J.M. Whittaker, the son of the famous Whittaker of Whittaker and Watson, as to how it was found, and he wrote to me the following. When the Royal Society asked me to write J.N. Watson's obituary memoir, I wrote to his widow to ask if I could examine the papers. She kindly invited me to lunch, and afterwards his son took me upstairs to see them. They covered the floor of a fair-sized room to a depth of about a foot, all jumbled together, and were to be incinerated in a few days. One could make lucky dips, and as Watson never threw anything away, the result might be a sheet of mathematics, but more probably a receipted bill or a draft of his income tax for 1923. By an extraordinary stroke of luck, one of my dips brought up the Ramanujan material, which Hardy must have passed on to him when he proposed to edit the earlier notebooks. So this is the course of this material that finally wound up in the Trinity College Library, where I was fortunate enough to find it in 1976. Next slide, please. So what does the notebook look like? Well, you are undoubtedly will find it difficult to read anything on this page. What I will tell you is that there are many amazing things in this notebook. In particular, on this page, right at the top, the first line of this page relates to a story about the theory of partitions that seemed to have started in 1944 when Freeman Dyson made certain conjectures about the classical partition function and was unable to prove them. And in the early 1950s, Swinnerton Dyer and Oliver Atkin were able to provide a proof. The most amazing thing about that entire story is that on this page of the Lost Notebook, the entire solution that was eventually found by Atkin and Swinnerton Dyer, although not in an obvious statement, the entire solution rests on this page, so that Ramanujan had actually had answered the conjectures of Dyson 25 years before Dyson made the conjectures. In addition, Dyson made an extremely unusual conjecture about something called, he was unable even to define it, but it was related to Ramanujan's partition congruences, and it was called the crank. Frank Garvin, my student, eventually unraveled this mystery from the second equation on this page, so that Ramanujan not only anticipated Dyson's conjectures, he anticipated Dyson's conjectures about conjectures. So this is quite an amazing page of mathematics, and it is probably one of the most interesting pages in the Lost Notebook. Next slide, please. So many pages are organized as you see them here. There is an equation after an equation after an equation. Sometimes they are related to one another, sometimes they are not. Next slide, please. Many of the pages of the Lost Notebook are completely chaotic, as you can see in this one. In particular, there are no assertions being made. Lots of calculations, some of them written at an angle, some fragments of infinite series and infinite products, but nothing that is comprehensible or that you can tell what Ramanujan was thinking about. Presumably, these were pages of scratch notes on which he was formulating and calculating in order to come up with the ideas of the more well-organized pages of the Lost Notebook. Next slide, please. So this, again, you see here the somewhat chaotic aspect of the notebook, a long string of calculations, but never set equal to anything, so one does not know what is happening. So about 40% of the Lost Notebook looks like the last two pages. 60% looks like the well-organized pages that I showed you before. Next slide, please. So one of the most intriguing features of the Lost Notebook stems from G.N. Watson's own analysis of the last letter of Ramanujan. Watson proved most of the results that were in the last letter, but the idea of the Mach theta function being something very much like a classical theta function, but not equal to it, is something that Watson pretty well took care of with regard to the first 5 functions, which were called the third order Mach theta functions. But in examining the fifth order functions, Watson was rather gloomy, conjecturing that there were no nice formulas that would allow one to do the analytic analysis of the fifth order functions. As you functions. Next slide, please. Okay, so basically here are the fifth order Mach theta functions. These, I've written them out so that they are much clearer than they were in the letter. And there is a second class of fifth order functions, but I will only talk about these 5 functions. Next slide, please. So I've just copied just a couple of equations from the middle of one of the pages in the Lost Notebook. I will show you this in more detail on the next slide, but I wanted you to see it in Ramanujan's actual handwriting. This is the formula that Watson conjectured didn't exist. Next slide, please. So this is now written out in a form where you can actually see what's going on. This phi 0 of minus q is one of the Mach theta functions that I listed earlier. And the point is that if the bottom of equation, it is equal to 2 expressions. One is a classical modular form, and the other one is what one would call an Appel-Lerch series. This sort of series is what Watson had found for the third order functions, and he conjectured there were no such results for the fifth order functions. And yet here in the Lost Notebook, Ramanujan sets it out as they exist, so that you have now these formulas of this nature. And the quest was to actually prove these because Ramanujan proves nothing in the Lost Notebook. He only lists formulas, and they are almost 100% correct. There are a few things where one at least has questions about what he was writing down, and I will talk about that later in the talk. But for the most part, everything he's written down, Bruce Baird and I have proved in these 5 volumes, many times with the help of many other mathematicians who have studied the Lost Notebook. Next slide, please. So here is an equivalent formulation as well, done in terms of Lambert series and of these Appel-Lerch series. Next slide, please. So, interestingly enough, these conjectures that are of Ramanujan that were eventually proved by the American mathematician Dean Hickerson, can be stated purely in terms of arithmetic. And so Dyson, in his conjectures about the Ramanujan congruences, defined a very simple aspect of classical partitions. So you see at the bottom of the screen there, the partition of 14, I guess it is, as 5 plus 4 plus 2 plus 1 plus 1. So the rank of a partition is the largest part minus the number of parts. And so the partition you see at the bottom of the screen has largest part 5 and also has 6 parts, so its rank is -1. Dyson's conjecture about the partitions was that if you look at the partitions of 5n plus 4 and classify the rank of each one mod 5, it splits those partitions into 5 equal classes, thus proving the first of Ramanujan's conjectures. So next slide, please. So there are 2 Mach theta conjectures proved by Dean Hickerson. I will only recount the first one to you. Good. So if you look at the rank of the partitions of 5n that are congruent to 1 mod 5 and subtract partitions of 5n congruent to 0 mod 5, this equals the number of partitions of n in which the largest part is odd and each part is greater than or equal to 1/2 the largest part. In other words, Ramanujan's very esoteric conjectures, which stayed open for 15 years after they were unearthed before one could prove them, can be stated just purely in terms of arithmetic. So next slide, please. So the study of these functions really got going with, has as its basis work that was done by W.N. Bailey. Next slide, please. So I don't want to go deeply into the weeds on anything here, except to say that W.N. Bailey, in studying the work of Rogers and Ramanujan, distilled it into a nice transformation of infinite series. Next slide, please. And so this is deeply in the weeds. Let me only tell you that it produced such a complicated formula that Bailey found it embarrassing. And so in his paper, which is discussing the Rogers-Ramanujan identities and extensions of them, he lists the formulas that you see here and says that you can construct certain results from them, but that it is too messy to be worthy of actually writing it down, which was very fortunate for people who came after him, because writing it down produced something quite striking. Next slide, please. Namely, what Bailey did was to look at sequences of rational functions, alpha n and beta n, related by this finite summation formula. Next slide, please. And what Bailey refused to write down because he was embarrassed by it is something that is one of the most powerful tools in this entire subject in studying the work of Ramanujan. Namely, it is an iterative technique for producing new Bailey pairs out of old Bailey pairs. So what I want to stress here is really the top line. Namely, from a given Bailey pair, you can produce a new one. It is definitely down in the weeds to see what it is, but the idea of this infinite sequence, because obviously if each one produces a new one, the new one will produce one after that, and you will have an infinite sequence. And indeed, there are formulas to reverse the sequence so it can be a bilateral sequence. Next slide, please. So the iterative form of Bailey's lemma produces one of the striking generalizations of Rogers Ramanujan identities. So there's a multiple series analog of the famous Rogers Ramanujan functions, and that is what you see on the screen here, all produced by the fact that there is this iterative form of Bailey's lemma. If he had been willing to be embarrassed by it and actually write it down. Next slide, please. So in order to treat the fifth order Mach theta functions, one looks at the following relationship, which greatly simplifies what the formula for Bailey's lemma looks like. When you let some of the parameters tend to infinity, you get this very neat form that we see at the top of the slide. And the beta n is now this reciprocal of this finite product. And the question is, what is alpha n? So next slide, please. So the fortunate advantage that we have over Ramanujan currently is that we have computer algebra. So Ramanujan was extremely good at calculating, but the difficulty and the extreme extent of calculation is nearly impossible for anybody to do by hand, even for Ramanujan to do by hand. But the use of modern computer algebra allows us to see things that Ramanujan apparently did not see, because the indication right in the bottom slide here, incidentally, there's the q to the 2 and a subscript 6 should be q to the 26th. But you see these nice expressions involving the negative of the squares, -1, -4, -9, and -16. That leads us to the formula, and indeed eventually leads us to Dean Hickerson's proof of the Mach theta conjectures. Next slide, please. And so when you put them in, the formula that you get for the Mach theta functions you see at the bottom of the screen here. And this is the, so to speak, the key to open up the Mach theta conjectures, and thus to put them on the same sound footing that Watson had put the original third order functions on. So next slide, please. So Frank Garvin, in his PhD thesis, was able to actually prove, or at least set up, an understanding of all of this, so that that he could not only explain the Atkins, Swin, and Dyer proofs, he also was able to explain what the crank is. Next slide, please. No, next. Okay, Dyson conjectured that this rank split the partitions into 5 equal classes, and there is a similar partition for P of 7n plus 5, that it splits into 7 classes, and P of 11n plus 6 splits into 11 classes. But Dyson conjectured this for 5 and 7, but the same idea didn't work for 11, and this is what led to his famous concluding paragraph of his initial paper. Next slide, please. I hold, in fact, that there exists an arithmetical coefficient similar to, but more recondite than, the rank of a partition. I shall call this hypothetical coefficient the crank, and denote it by m of a little m, q, and n, the number of partitions of n whose crank is congruent to m mod q. And then he states a number of things that he wants this capital M function to satisfy. And he said, whether these guesses are warranted by the evidence, I leave to the reader to decide. Whatever the final verdict of posterity may be, I believe the crank is unique among arithmetical functions, and having been named before it was discovered, may it be preserved from the ignominious fate of the planet Vulcan. Next slide, please. So we're back to the page that I showed you earlier, and the second equation that is listed there, and the formula for that little f of q is, as Frank Garvin has shown, precisely what's necessary to find and deliver the crank of a partition. Next slide, please. So, yes, so in summary, Frank Garvin basically saw how this worked, was able to prove these assertions by Ramanujan, and thus set up the discovery of the crank of a partition. Next slide, please. Yes, I just said that. Next slide, please. Okay, Hadamard products for entire functions. There are some really wild formulas in the Lost Notebook. Next slide, please. Here is one of them. So this is an absolutely weird thing, namely the series on the left is the series in the Rogers-Ramanujan series. If you set A equal to 1 or A equal to Q, these are the famous Rogers-Ramanujan identities. And they are equal to infinite products that look nothing like the infinite product on the right-hand side of the equation. Indeed, if you look at that, it gets weirder and weirder and weirder. The denominator series in the infinite product, where these y1, y2, and y3 are, he lists them as you see, y1, y2, y3, and y4. y2 is identically 0. And y1 is made up of something related to a famous identity of Gauss. Y3 is even stranger, and y4 is the product of y1 and y3, and he stops right there. So, next slide, please. So basically, the secret to this lies in the study of entire functions. What Ramanujan was doing, whether he knew all of the formal and rigorous aspects of entire functions, he was looking at that series not as a function of Q, but as a function of A that was an entire function as long as the absolute value of Q is less than 1, and following the classical idea of an entire function somehow being, this is not rigorous, but effectively an entire function is something like an infinite degree polynomial. And so that is the expansion of this entire function, and that is what Ramanujan came up with there. Something that takes a long time to prove. Next slide, please. Basically, the proof relies on looking at a function, and this is a weak case of Hadamar's factorization theorem, where you do not need correction factors to produce convergence, as long as you have these zeros, this series of the reciprocals of the zeros converging absolutely, then you have this expansion for the entire function. And this is precisely what Ramanujan was working out in that case. Next slide, please. So I won't go into great detail except to say that there are polynomial approximations to these infinite series, and as a result, one is able to study the zeros of these polynomials, and with enough effort, you can show that the zeros converge to the expressions that you saw on the first slide for the y1, y2, y3, and y4. But it really is quite an amazing discovery, and not anything that seemed at all plausible. In fact, many of the things that Ramanujan looked at are things that come as a total surprise, and as the genius of the man is really hard to fathom for mere mortals. Next slide, please. Basically, the study of the Szego polynomials, the advantage one has is one understands them as orthogonal polynomials with simple zeros on the negative real axis, and a careful study of what happens when n tends to infinity yields Ramanujan's identity. Next slide, please. So one of the fascinating aspects of having spent so much of my life studying this notebook is trying to think up how Ramanujan actually thought about things. And so I have fallen into traps several times, and so I thought I would take the most egregious example where I made a mistake and or mistook how Ramanujan did things, or at least I now believe I mistook it. And so next slide, please. So here's another page from the Lost Notebook. This page is devoted entirely to continued fractions. So Ramanujan is most famous for what is called the Rogers-Ramanujan continued fraction. On this page of the Lost Notebook, you see listed a lot of continued fractions and identities for them. And I looked at them first when I saw them and really had no idea about how to handle them. Next slide, please. However, on an unrelated page, in the middle of the page, you see something that says if G of something lambda equals 1 plus, right in the middle of the page, there's a formula for a continued fraction. And I thought, aha, this is what he used to do that other page. And so I then worked out a complete analysis of how you could prove the vast majority of formulas on the other page by looking at this particular one formula in the middle of this page. And I thought, well, at long last, at least I've explained something. So next slide, please. So this is what the formula is on the previous page. That is, you see a continued fraction, and it has 3 free parameters, A, B, and lambda Q is sort of the standard base here, but the A, B, and lambda can be varied with keeping Q fixed, and you get, as I say, the vast majority of formulas on the previous page. I was sufficiently proud of this that I presented it at a talk celebrating the 100th anniversary of Ramanujan's birth. Next slide, please. So here, for example, is one of the formulas from that page. And as you see in the square box, I've indicated how one chooses the parameters of the capital G function in order to produce this result. Next slide, please. And here's another one. And again, I've indicated how it goes so that you see I really thought I was onto something because I could get all of these formulas out of special cases of this master formula. Next slide, please. And now one more on that. Okay, next slide, please. So after confidently deducing all of Ramanujan's list from the G of A and lambda continued fraction, as I presented it, the late K.G. Ramanathan, a good friend of mine, was sitting in the audience, and he pointed out that in 1936, Atlee Selberg had done the entire list in a much more Ramanujan-like manner, not deduced from the master formula at all, but done in a way that looked much more like what Ramanujan would have done. And so at least I must say that when I came to the end of that adventure, I felt fairly confident that my initial belief that I had solved the one mystery was now thrown back into doubt. Next slide, please. So Ramanujan's mischievous ghost. So this is a story connected with the 100th anniversary celebration that I was just talking about that took place. There were celebrations indeed all over the world. I attended maybe 6 at least conferences, maybe 7 in in India in December of 1987. And also there was a major conference at the University of Illinois. My colleague Bruce Baird is there. And at this conference, many people were speaking about Ramanujan. Next slide, please. Just before his talk at the 100th birthday of Ramanujan at the University of Illinois, Bill Gosper showed me two beautiful identities he had just discovered and proved. Next slide, please. Here they are, just things involving classical theta functions and really series with the elegance of the Rogers-Ramanujan identities, in addition to which there's a free parameter. Next slide, please. I was compelled to point out to him that both were in Ramanujan's lost notebook. And during Gosper's talk, he described his discovery and acknowledged Ramanujan's priority with the following remark. Next slide, please. How can we love this man when he reaches out from the grave to snatch away our best results? And so Ramanujan, one of the things that one is constantly aware of in the Lost Notebook is how many things Ramanujan discovered decades prior to anybody else even thinking about them. And many of the things he discovered, nobody else thought about until the Lost Notebook was actually brought to light more than 50 years after his death. Next slide, please. So, I mentioned earlier that almost everything in the Lost Notebook is true. However, there are one or two formulas where I suspect that he had figured out something on his slate, and in making a copy into these sheets of paper, he failed to record maybe an infinite product that was necessary or some other component which can be easily supplied. On the other hand, there are some things that require a more quizzical look. Next slide, please. So this is a page you've seen before. This is a page with these continued fractions in it. And right down near the bottom of the page is one continued fraction that I will highlight for you on the next slide. Next slide, please. That is this assertion that 1 minus x plus x cubed minus x to the 6th plus ... equals this continued fraction. So, and there are 3 dots connected with the continued fraction so that you can see precisely what is going on. And I'm not sure anybody sees the continued fraction at the moment. There it is again. All right, good. So the 3 dots are where the mystery lies. So when you see 3 dots, it generally means things go on as before. So when you're looking at the continued fraction, the next line is probably 1 plus x to the 6th plus x to the 7th with a bar, and then going on to x to the 8th plus x to the 9th, etc. X to the 7th plus x to the 8th, x to the 8th plus. And on the left-hand side, the exponents are clearly the famous triangular numbers. So 0, 1, 3, 6, 10, 15, etc. So next slide, please. So if you continue the continued fraction as it goes, the first 4 terms of the series are this, but it doesn't, the 3 dots are not what you would hope for, because instead of the next term being plus x to the 10th, it's plus x to the 8th minus x to the 9th minus x to the 10th. So what Ramanujan wrote down, well, let me see the previous slide. What he wrote down is true, but the 3 dots are extremely misleading. The 3 dots, if you look at what you expect is the next term in the series is plus x to the 10th. But next slide, please. But you wind up with x to the 8th minus x to the 9th and minus x to the 10th. so that what Ramanujan was saying is technically true, but it was highly misleading. Next slide, please. So that covers everything that I wanted to tell you about just some aspects of the Lost Notebook. There are many other formulas. There are many other exciting and surprising results. But I hope this wasn't too far into the weeds. The main thing I wanted to do was to communicate the excitement, the surprise, and the amazing fact that what he wrote down in 1919 and 1920 lay dormant for many decades, and only really since the rediscovery of his writings have we unearthed many of the mysteries connected with his work. Indeed, if you think about it, the fact that he wrote 120 pages, 40% of which are incomprehensible because they really have no assertions on them, and think about the fact that it took 5 volumes and 2 mathematicians more than 20 years to supply a complete account, you recognize that this was a man of special genius, something the late Mark Kotz would have called Ramanujan a magical genius. Kotz distinguished ordinary geniuses from magical geniuses. Ordinary geniuses are people who are just smarter than I am, but if I had worked really hard and really long, I might have come up with what they came up with quickly. Magical geniuses are people where you really have no idea where they got their information, their ideas, how they came up with it, how they came up with the assertions they found. And Ramanujan, if anybody has ever been in the magical genius class, it's Ramanujan. So I thank you very much for your attention. I will be happy to try to answer any questions.
Thank you very much. I think Dr. Venkateshwaran will coordinate the questions.
Yeah, Dr. Ramanujan, why don't you start?
Yeah, sure. Okay, Professor Andrews, thank you very much for that exciting session, I must say. One question, historical nature. Ramanujan was writing to Hardy. We look at Ramanujan's letter to Hardy and the kind of mathematics that he's talking about. They're very classical in some sense. I mean, Q series, partitions, many of those things.
Yeah, very classical.
But then when you're talking about the letter when he was on his deathbed and the kind of mathematics that you're talking about in the Lost Notebook, it's very different kind of mathematics. I mean, mock theta functions.
So I do. So yes,
I mean,
it is very different. But there is a very natural path from, say, the notebooks that he wrote before he went to England to what he wrote afterwards. There is a very natural path there, which led him into things that have really, in terms of intense interest. The mock theta functions are of extreme interest currently, and using much of modern mathematics that Ramanujan would have not been familiar with. But Ramanujan had some. When I call him a magical genius, I'm not being flippant or funny. I mean, he had insights that we just do not know what they were. They certainly foreshadow many modern techniques and ideas that he certainly gave no hint of knowing the techniques, but it's impossible for him to have written down the things he wrote down without having some understanding that probably if he could communicate it, somebody else could translate it into rigorous modern mathematics. But I mean, if you think about the classical case of, say, the story of the asymptotic formula for the partition function, there it really was, would say necessary for G.H. Hardy to be there to supply the esoteric aspects of complex analysis to make the thing go through. But Hardy never in a million years would have come up with precisely what Ramanujan had in the way of an idea as to how the whole thing went.
When you were looking at the Lost Notebook and the papers, did you see Ramanujan working on some papers, I mean, of the kind that he was publishing? Because these notebooks, they just list of formulas. But was he also trying to publish some of these things?
The notebooks are all lists of formulas. I mean, one really does not know. I suppose one suspects that he did much of his calculation on a slate, and the paper was very expensive. And so, if you recorded a theorem and you knew the proof, then as long as you had the theorem down, it would be an adequate mnemonic for producing a proof if anybody asked for it. Of course, neither he nor Hardy expected him to be dead at age 32, so that there would be, if he'd lived to a ripe old age, there'd have been plenty of time to write down the proofs.
Yeah, thank you. What about Rademacher was looking at Rogers Ramanujan identities and working on them also, right? Did he also work on the Mach theta functions? Did he hear from Hardy?
Rademacher was fascinated with the Mach theta functions. And the reason that I knew what the Mach theta functions were is because Rademacher, who is my thesis advisor, asked me to follow up on one aspect of the Mach theta functions. And so in the early 1960s, if there was a less fashionable mathematical topic than Mach theta functions, I can't think of what it was, but Rademacher thought that they were extremely interesting. And so that's why he assigned that as a thesis topic to me. And so it was a huge advantage for me, because when I found the Lost Notebook in the Trinity College Library, the first thing to say about it is that the phrase Mach theta function is nowhere in the Lost Notebook. Those three words do not appear there. And so if you don't know what the Mach theta functions are, you won't see them, because they just look like any other sort of Q series. And so it was my great good fortune that I knew exactly what they were, and there they were. And so that was something, there's various fortunes, good luck we have in life that we are really not responsible for, but are very grateful for. And that was certainly good luck.
Thank you. Over to Dr. Venkatesh.
Yeah, thank you. There is one question which has come from one of the participants, which is what's the closed form for the last continued fraction you showed in the last slide, sir?
Okay, so the answer is that I do not know of any closed form. In other words, I only showed you out to x to the 10th, but I have computed it farther than that, and it doesn't seem to have any sort of nice aspect to it. It's one of those things. I mean, I don't know. He may have written it down that way and been doubtful as to whether maybe he made a mistake farther on, but thought it was interesting enough to note it down, stopping at 6, where it looked quite natural. If you recall, in the bit I did on the Adamar products thing, where he had Y1, Y2, Y3, and Y4, the reason he stopped with the first 4 Ys is because Y5 is a massive monster of a thing that you can dig out with computer algebra. And whether he knew it or not, it would have filled up an entire page for him to write it down. But the first 4 of them are very lovely, and that's what he put down. And I have the feeling he may have done that for this series as well, but I know of no closed form for it.
Yeah, now there is one more comment one of the viewers have put, which is, Srikumar, can you flash that? How was the approximation that led to Roger Szego polynomials done?
Okay, so basically, it took me it took me a long time to see this as an entire function. Once you see it as an entire function, then the next question is you can look at it and see where its zeros are. And so another fortunate aspect of life is that I had spent the year that I discovered the Lost Notebook, I was on leave from Penn State and spending a year at the University of Wisconsin as the guest of the late Richard Askey. Richard Askey was an expert on orthogonal polynomials, and so he and I were trying to look at the merging of the Q series types of things that Ramanujan did and the work on orthogonal polynomials that was the specialty of Richard Askey. So that by the time I got to the Trinity College Library in 1976, I had also had a reasonable education with regard to orthogonal polynomials. And seeing that the zeros of this function, at least according to computer plots, were simple and on the negative real axis, it occurred to me that maybe orthogonal polynomials would be the secret. And once you have that idea, then you realize that the approximation to this series is a class of orthogonal polynomials, and consequently, the zeros of it will, of necessity, be naturally simple zeros lined up as you would like, and all you need to do is to take care of the limit as n goes to infinity to make the thing actually work out.
Yeah, that's nice. Jam? You have to unmute, Jam. You have to unmute. You are on mute.
Yeah. Okay. Sorry. Yeah. I, in a sense, the discovery of the Lost Notebook is reminiscent of the discovery of Beethoven's unfinished symphony.
So the first time I spoke in public about this, I was introduced by Emma Lamer, who was D.H. Lamer's wife at the University of California. So this was a talk in Seattle in the summer of 1977. It was my first major talk on this. And when she introduced me, she said, opening a box and finding Ramanujan's Lost Notebook should be comparable to opening a box and finding Beethoven's 10th Symphony.
Right. Yeah. So that's why I said the project is something like taking up that unfinished symphony and working on it.
It was quite a moment.
Yeah. So
it was such a thrilling event. My wife and my two daughters were accompanying me in Cambridge on the day that I discovered this, and I was so thrilled by it that I took them punting on the cam and was so arrogant in my managing of the punt that I fell in the river. So that was my celebration of discovering the Lost Notebook.
So there are many teachers in the audience, so I wanted you to remark to them, to the teachers, especially on what it might mean to, in terms of listening to the students and their work, the creativity that there may be. So, yeah, any remarks you have would be welcome.
So I see one of the questions. Imagine if Ramanujan was alive today, how would our world have been different? Probably the mathematical world would have been different. I don't know. I'm not sure how much effect. Mathematics has sort of a long run effect on things, but it's hard to say what effect it would have had. It's hard to say what effect it would have had if he had a normal life. We really do not know where he would have gone or what he would have done. So,
there was one question that Ramanujam also was trying to present, which is basically like on maths education. If you can throw a bit of light, because there are a lot of maths teachers who are in the audience, that would be very interesting.
So in, I think the year 2002, I think it was, I attended the National Science Congress in Lucknow, and spoke on Ramanujan. And the afternoon, the mathematics session was devoted to education, and I was asked to say a few words. So my first bit of advice to you is never listen to a word an American tells you about education. We've had some of the worst crackpot ideas over here. It seems to me your education system is highly developed. Sometimes it might be a little rigid, but it is certainly an efficient system that has produced many fine mathematicians. And so far as the general public goes, I think that it is something that you can be proud of. So also, one of the things that had one of the other aspects of education that I'd followed up on is a book by James Tooley called The Beautiful Tree. It is basically about private schools for elementary children that are run in some of the poorest parts of cities throughout India, Nigeria, other parts of the world, where the poor people of the world have been able to surprisingly produce efficient schools for their children, and that are significantly superior to government schools. So it's a fascinating story. When I was at the International Congress in 2010, I think it was, in Hyderabad, that is where this book started. And so I went to his foundation, and I was given a tour of some of these schools in the very poorest parts of Hyderabad, and it was an inspiring and fascinating experience. So I think that basically the world has much more to learn from India than India has to learn from the world about math education. Basically, I'm a traditionalist, and so I believe that the thing we need to focus on is the content of the subject. And if you are someone who has empathy and likes students and likes to teach, those are the real requisites. The efforts at putting all sorts of hardware in front of 6-year-old students seems to me to be a very unwise project. But there are many people in the world who disagree with me on that, probably many more in the United States than in India.
Very, very nice. I think that's a very interesting point. I think I also visited that Hyderabad school. It's a very inspiring place where underprivileged children are given education.
Stunning and inspiring.
Yeah. Okay. I think then we have come to the last part of our session. So, Ramanujan, can you thank the speaker, and then we can wind up the session? Dr. Ramanujan? I mean, I think we have come to the last part of our session. We can thank the speaker and then wind up the session. Would you join in?
Yeah.
No,
yeah,
I think.
Yeah.
Please,
Is Dr. Parashar expected, or okay? Yeah. Anyway, it's my pleasure to thank Professor Andrews, and yeah, thank you very much for giving us this wonderful presentation. It's perhaps the great tribute that we can pay to Ramanujan on the occasion of his 100th anniversary of his death, and a great way to remember. And you made us almost relive that moment of surprise when you found the book, and all the exciting discoveries since then. These are Ramanujan is always inspiring, and every revisit and every time we look at any of his work, it's deeply inspiring for all of us. And thanks for giving us this wonderful moments. Thanks very much, Professor Andrews. Thanks, Dr. Venkateshwaran.
Thank you. Thank you.
And I, on behalf of Vigyan Prasar and also the organizing committee of Ramanujan Yatra, would thank Professor George Andrews for this very wonderful talk, Dr. Ramanujam for conducting this program and also helping us organizing this special session, and also all our colleagues, Sri Kumar and Bhaskar and others at Vigyan Prasar for the technical support, and all the participants who are there in huge numbers in both Facebook Live and also YouTube Live and the India Science live relay. Thanks, all of you. And then we can see in the comment section that quite a lot of people have commented that has been a very nice lecture and an excellent program. So thanks everyone for this program. Thank you. With this, we will wind up today's session. Thank you, sir. Thank you very much.
Thanks. Bye-bye. Bye-bye.
Bye.